you change everything to mass after you assume a 100-gram sample, you want to change everything into its individual mole value. So for this, for carbon, right, 1 mole over 12 grams, yeah, 12.01. For hydrogen, we're going to do 1.01. Also, for while the whole time we're doing this, please someone else also be doing the calculator stuff, or multiple people be doing the calculator stuff, so that we can make sure that we're not messing up at all. Oxygen. All right. Let's get this out of the way. If you do get something drastically different from what I get on my calculator, let me know. For carbon, we're going to do 41.4 divided by 12.01. You can come up with 3.44 moles. For oxygen, for hydrogen, we just assume it's 3.5 moles. And for oxygen, 55.1 divided by 16. It's also 3.44 moles. Okay? Cool? You good? All right, so once you're at this number, you guys remember what to do now? Is it coming back at all? Divide by the smallest moles. Cool, awesome. So you can divide this by 3.44. Divide by 3.44. Divide by 3.44. All right, so the top is just 1, bottom is 1. 3.5 divided by 3.44 is going to be almost negligible. It's going to be like 1.01. Cool. So now what can we say the empirical formula is? 1, 1, 1, right? These are all the numbers that you're going to put on the bottom of every. This one can just round up to 1, but this is what's going to put CH O. Cool? Are you good? All right. So yeah, number 1 is A. Cool? All right, moving on to number 2, and there's no eraser. Perfect. Awesome. Yeah. Nice. Let's use this random paper from my bag. All right, number 2. How many hydroxide ions are in 2.5 moles of magnesium hydroxide? So 2.5 moles of magnesium hydroxide. When they ask you how many ions are in something, what is that the same thing as almost asking you? Molecules, right? So if they're saying how many ions, it's essentially how many molecules of this guy. When magnesium hydroxide breaks up, it breaks up into 1 magnesium, right? For every, there's 2 hydroxides for every 1 magnesium, correct? So if I have 2.5 moles of this whole thing, how many moles of hydroxide am I going to have for every 2 moles? If it's a 1 to 2. So if I know 2.5 moles of MgOH, 2, that means for every 1 mole of MgOH2, I have 2 moles of OH. Does that make sense? Cool. So in total, I have 5 moles of OH. How do I go from moles to atoms? You guys remember this one? Avogadro's number, right? So? All right.
Do you hear anything?
Cool. All right, so we've got.
Oh, no, let me turn it on.
Nice. All right. 6.02 times 10 to the 23rd atoms. All right? And you can tell that this 6 times 5 is going to be like 30. So it's going to be the answer choice that has a 3.0 in it. Do any of them have 3.0 in it? Yeah. Right? 3.0 times 10 to the 24. You can do it on your calculator again, but it ends up being this answer too. So there are 3.0 times 10 to the 24 ions. And that is answer choice D. Any questions on that? All right, cool. Moving on to number 3. All right, sample consisting 1 mole NaBr and 0.3 moles of Ki. Cool? So 1 mole of NaBr. And 0.3 moles of Ki. And they want the percent by mass of iodine. Well, you're obviously going to want to break everything into however many moles of everything you have and to however many grams of everything you have. So I know here I've got 1 mole of sodium and 1 mole of Br, 0.3 moles of potassium, and 0.3 moles of iodine. Cool? So you're going to want to change all of that. 1 mole of sodium is just 23 grams. 1 mole of bromine is 79.9 grams. 0.3 moles of potassium is right here, 0.3 moles. So we can multiply it by 1 mole of the weight of potassium, which is 39.1 grams. Do the same for iodine, and iodine is 126.9. That comes out to 39.1 times 0.3. It's 11.73 grams. And 126.9 times 0.3 is 38.07. All right, so if I want to find the percent by mass of iodine, what am I going to do with all these masses? Add them all up and then just divide iodine by the entire total times 100, because that's what percent by mass is, right? So 38.07 plus 11.73 plus 79.9 plus 23 is 152. So we can just do 38.07 divided by that answer times 100. Make sure everyone is doing this at the same time as I am, or just to make sure. And yeah, it comes out to 24.9%, which is answer choice A. Cool. Hey, can we make sure, can I get an eraser, please, from someone downstairs? Yeah? Yeah, if you have one at all, because I can't keep using this. All right, so number 5. Jesus, man. 4? Wow, thanks, guys. I forgot how to count. All right, number 4. What is the concentration of chloride ions in a solution formed by mixing 150 mils of 1.5 molarity NaCl and 250 milliliters of a 0.750 molarity solution of MgCl2. All right, so if I want to find the concentration of chloride ions, the formula for concentration is molarity equals moles divided by liters, right? Do I have the total liters of the solution when I mix it together? Am I given that information? I mean, they give me 150 and they give me 250. So if I add them up, that's the total volume, right? So I'll have 400 milliliters, which is 0.4 liters. Yeah? So now I just got to find the moles of chlorine up here. So let's do that from finding both of these. So set up molarity equations for the first one, 1.5 m NaCl, and I have 0.150 liters of it. So how many moles of NaCl do I have? So we can do 1.5 times 0.150, 0.225. So if I have 0.225 moles of NaCl, how many moles of Cl do I have? Usually I just have 0.225, right? Because everything's 1 to 1. It's not like magnesium hydroxide before. Before we had 2 hydroxides for every magnesium hydroxide. So we had to multiply that mole number by 2. But here, since the subscripts are just 1 sodium and 1 chlorine, we can also assume there's 0.225 moles of NaCl. So far I have, thanks a bunch. So far I have 0.225 moles. We have to add something else from the other answer to find out the total. Second answer is 0.750 m equals some amount of moles over liters. I have the liter value. So now I can do 0.750 times 0.250. And that's 0.1875, right? Moles of MgCl2. Now this is the case just like we did with the hydroxide. For every 1 whole mole of this, there's 2 moles of chlorine, right? So I can do the whole math thing where I'll multiply out, 1 mole of MgCl2 for 2 moles of chlorine. You can do this. You can write it out like that if it helps you remember it. But I feel like if you understand that the subscript is 2, so if I have a certain mole value of this whole entire thing, I'm going to have double of chlorine. Cool? So you can multiply like this if you want, though, because this works every time. Equals 375 moles. So now I've got 375 moles. So 225 plus 375, 0.6. So in total I have 0.6 moles. And 0.64 is 1.5 molarity. So the molarity of the chloride is 1.5, which is answer choice C. Any questions on that? Also, if you guys didn't already notice, I wrote the problems that we're going to be skipping on here, the right upper corner. So make sure you write that down. What's up? It was 1.5 molar, so C. All right, number 5. Barium chloride reacts with sodium sulfate according to the following equation. Okay? I'm not going to write the equation down because you guys have it and it'll take too long. But the student mixes a solution containing 10 grams of BaCl2 and this has a molecular weight of 208.2 grams. And a solution containing 10 grams of Na2 SO4, and its molecular weight is 142.1 grams. And he obtains 12 grams of BaSO4. SO4. And that has a molecular weight of 233.2. Cool? And we want to figure out the percent yield. So percent yield equals actual over theoretical times 100. They already gave us the actual. They already told us what he actually yielded. So the 12 is already here. We've just got to find theoretically how much he would make. So to do that, we've got to figure out a limiting reactant, right? So we've got to see how much this would possibly give us and how much this would possibly give us and see which one is less. Okay? So let's go ahead and do that. So for the first 10 grams of BaCl2 times 208.2 grams over 1 mole. So we got to change it to moles. Look at the mole ratio between BaCl2 and BaSO4, and it's just 1:1. Multiply that by the mass of BaSO4, which is right here. Let me erase this since we already know what that is. And that should equal our grams of BaSO4. And the next one, same thing. And that's 10 grams by 1 mole of it. And look at the mole ratio. I think it's the same again. Again, times the mass of barium sulfates. And that's going to equal a gram value of barium sulfate. Has anyone got the value for the first one already? 11.2 for the first one. Anyone do the second one? Just shout it when you've got it. Okay, I'll check. Yep, I got the same thing. So 16.4. So which one of these things gives us less moles of product? The first one, right? So the first one's going to limit how much we can make. So that's the most we could possibly theoretically make. And we said percent yield is the actual over theoretical times 100. So percent yield actual over theoretical, and the actual was 12 grams. And the theoretical was 11.2 grams times 100 equals it's something over 100%, right? So if you look at the answers, the possible answers, you had 3 numbers that were under 100. And the last one was the isolated barium sulfate was most likely wet, since the yield would otherwise be greater than 100%. Cool? So you calculated that just for the sake of having a number. Let's just see what it was. Did you guys get 107%? Cool. So he got 107% yield, so that means he did something wrong. Probably had a little water on it that increased its mass, but yeah. Cool. All right. Anyone else need it? All right. All right. Number 6. Which solution has the highest boiling point? 1 mole acetic acid, CH, which is CH3COOH, 1 mole sulfuric acid, 1 mole phosphoric acid, or 1 mole glucose. So what do we know about things with high boiling points? High molar mass, which is true. Yeah, they have high molar mass. What else? Something about hydrogen bonding. Excellent. So there's hydrogen bonding and high molar mass and lots of good intermolecular interactions, right? So if you look at number 1, CH3COOH, we know acetic acid. What is acetic acid? Is it weak or strong? It's a very weak acid, right? So it dissociates very easily. It doesn't hold on to its constituent members very well. So you know it's not acetic acid. Let's look at sulfuric acid. It could be sulfuric acid because you've got 2 hydrogens and you've got 4 oxygens. So those are 4 other possible locations for hydrogen bonding, right? Let's look at phosphoric acid, H3PO4. Wait, sulfuric acid is also strong, right? So we know that it's a very strong acid. Its members are very constituently held well. Yes? Acetic acid? Well, we know that acetic acid in and of itself is a very weak acid, and it's got 1 polar OH group that's on the side to itself, right? So it's only got essentially 1 spot where it could possibly hydrogen bond with other acetic acid members. So you know it's not that as well. So basically, also always when they're giving you acids, just think of like which is the strongest one. So the strongest acids are probably going to have the strongest intermolecular forces. Okay? So you can look at phosphoric acid. Phosphoric acid is another weak one. So sulfuric acid is the strongest possible acid out of all of these. Let's look at D, glucose. What is a characteristic of glucose? It does have a high molecular mass, right? But does it have any sort of dipole moments like the sulfuric acid would have? Is it as small and as polar? It's much larger, clunkier, right? It's much larger. It's got a lot of it's got a lot of carbon bonds that are going in a ring, so it's going to prevent it from having this super polar structure like H2SO4 would, right? And you know that polarity is key when you want to have a very, very high boiling point or a high melting point. Cool? So the answer here should be sulfuric acid, B. Any questions? Just remember it's the strongest. Yeah?
Why is that one over the H2PO4?
Phosphoric acid is another weak acid. Cool? All right, number 7. A white ionic solid is dissolved in water. Addition of a solution of sodium chloride to the solution. So you've got something in here, and I don't know what's in it, but I added sodium chloride. So in there I'm going to have Na pluses and Cl minuses, for sure, from the sodium chloride. Once I added it to that solution, there was some precipitate that formed. So what is the cation in the ionic solid? So a cation is something that's what, positively charged or negatively charged? Positively charged, right? So whatever in here, this X guy was positive, yes? Is a positive going to form a solid with a positive or with a negative? All right, it's going to form the charge with a negative, right? So what does that charge have to be up here? It's got to be negative, +3, +2, +1 to bond with Cl1 minus. It's going to have to be 1, right? So go ahead and look through your answers. Are there any of them with a charge of +1? There's Na and what? And silver. All right, so what did we go ahead and add in the first place to the solution? We were adding sodium chloride, right? Sodium chloride wasn't what was present, it's what we were adding, yes? So, and we already said that something else is in here, some sort of mystery zinc, though there's only 2 with a charge of +1, and it's sodium and silver. So it's got to be silver. Cool? Yes? All right, and I think that's C? Yeah. All right. Any questions? Yeah? All right, why was this silver? Well, we've got NaCl and something else in here that's a positive dude and a negative dude, right? Yeah? In precipitation reactions, what happens? Not just they break apart, but what happens? It's a double displacement, right? So the Na will be with the Y, and the X plus will be with the Cl, right? So in the end, it'll look like Na, and then whatever the Y minus was, and then the X with the chlorine. Cool? So you know for sure that the solid had to be over here. Make sense? All right, cool. What's that? Well, both members here, sodium positive and chlorine negative, the solid that you added to the aqueous solution, the members only had a positive 1 charge. There's no way they could have gotten, like if this was magnesium something, magnesium has a charge of 2 plus and bonded to something else with a charge of 2 minus, then the solid would have had to have been composed of something with that number of charge. And it's also just like, if you write it out like this and do the precipitation reaction equation where you just switch through things, you see that if I only have a +1 and a -1 here, there's the only possible way for this thing to bind immediately and produce a precipitate is if they had the same charge. Cool? All right. Erase this. An element is a solid at room temperature but soft enough to be cut with an ordinary knife. So it's soft enough to be cut with an ordinary knife, and it reacts violently with water. What elements do we know react violently with water? You guys remember learning that? Like the videos? All right, so the alkali metals, the very first group. Have you seen the videos of like them dropping like a gram of them in a tub of, like a bathtub, and it just explodes? Okay, well now you know. The group 1, all of the group 1 metals react super violently with water. So you know it's probably going to be a group 1 metal. And you know that it's soft enough to be cut, right? If something is a transition metal in that middle block, those metals, those heavy ones, do those tend to be soft? Like, can you get a silver chain and like mesh it up like Play-Doh with a knife? No, right? Unless you, okay, yeah, and I hope you don't do that. So we see we've got sodium, magnesium, copper, and Hg mercury. Cool? So we've already got copper out of the way, right? Because we know there's no way it can be soft. Yeah? And we know already that group 1 elements are the ones that act really violently, not group 2, which is why they put magnesium there. Cool? So you know for number 8, it's got to be sodium. All right? Any questions as to how we did that reasoning? All right. Let's see what time it is. Okay, cool. All right, number 9, a 0.1 molar solution of which salt is the most basic? All right, this is, you guys just did this recently, so let's see if anyone can help us out and see what we got to do. If I've got all these salts, what should I do to figure out which one's the most basic? Oh, God. Anyone? God damn it. Yeah? Yeah, cool. All right, so just break everything up into what it dissociates into. This dissociates into Na plus and NO3 minus. This breaks into Na plus and ClO4 minus. This breaks into Na plus and HSO4 minus. And this breaks up into Na plus and HCO3 minus. Cool? Does sodium change the pH of any solution? No, right? Sodium is completely neutral. And you can figure that out how? For every positive cation, for everything that's like a plus, just tack an OH onto it. If I tack an OH onto Na, it's NaOH, right? NaOH is a strong base or a weak base? Strong base. So when NaOH dissociates into sodium ions and hydroxide ions, there's no way for that sodium ion to go backwards or go against the grain of dissociation, right? So if it can't go backwards and go against the grain of dissociation, it can't act as the conjugate. Cool? So that's why sodium and things like chlorine, things that come from other strong acids or strong bases, they're never going to affect the pH. So you're going to be looking at the things that come from weak acids or weak bases. So this is probably going to make, so you know all the sodiums are not affecting. Now let's look at NO3. NO3 comes from, if you see a minus, just tack an H on, comes from HNO3. Is NHNO3 strong or weak? Nitric acid? It's very strong, right? So this isn't going to be able to go backwards. So it's also going to be neutral. So this thing is going to be neutral. Let's look at right here, NaHSO4. We already said sodium is neutral. HSO4, if it's negative, just add another H, H2SO4. Is that strong or weak? H2SO4 is a very strong acid, so there's no way for this guy to go against the grain, so it's not going to be able to act as the conjugate base. So we know that that's not going to be the answer. Okay, so let's look at both of these two. For the minus, this ClO4 is HClO4, and here we've got H2CO3. For both of those things, what is HClO4? If you look on, I'm pretty sure I got it on the front. Oh, no, I didn't write that down. Sorry, guys. All right, HClO4 and H2CO3. Does anyone know what either of those things is called? What's up? One is perchloric, right? So this guy right here is perchloric. Perchloric, is that strong or weak? Strong, right? So this guy is also not going to affect the pH. We eliminated 3 of them, so we know the last one is this one, but let's just go ahead and look through the reasoning. H2CO3, what is that? Carbonic acid. Carbonic acid is a very weak acid, okay? So when it dissociates into this, because it's very weak, because this is a very weak acid, this is the conjugate base, right? Since this is the conjugate base and its originator was very weak, it's going to be able to go against the grain and act as a base and make your solution basic. Cool? So that one is your answer. That's D. Cool? Any questions on it? Question? All right. Cool. All right, number 10 we're doing, number 10 we're skipping. So we're going to do number 11. A student determines the acetic acid concentration of a sample of distilled vinegar by titration of 25 milliliters of the vinegar. So we know we've got 25 mils of vinegar, which is acetic acid. And what's he adding in there? He's adding sodium hydroxide solution. Cool? Which error will give an acetic acid content for the vinegar that is too low? Okay? So he has to mess up some way so that he measures this as slightly less than what it actually is. Okay? So let's look through the answer choices and see which one that leads to. Some of the vinegar is spilled when being transferred from the volumetric flask to the titration flask. So if I accidentally spilled some of this, does it make sense that this number would probably end up being less if I calculated it? So A is a possible answer choice, right? Spilling some out is probably the easiest way to get an answer that's too small. B, the NaOH solution is allowed to stand for a prolonged period of time after standardization and absorbs CO2 from the air. If some of the NaOH absorbs CO2 from the air, I'm still going to have to be adding the same amount of NaOH to titrate this, right? If there are free NaOH molecules, they're going to be adding to this, right? I'm not adding carbon dioxide, I'm adding sodium hydroxide. So that answer is not going to affect how much I need of this. Cool? Let's look at C. The endpoint is recorded when the solution turns dark red instead of faint pink. Have you guys done the lab for Chem 2? Okay, so you know when you get titrations, you're supposed to get it as soon as it gets that very light color of pink, because that's exactly when the neutral equivalence point is reached. Cool? If that's exactly where the nuclear where the equivalence point is reached, if you keep adding NaOH until it's super dark pink, that means you have added way too much of this. If you've added too much of this number, you're going to read it as way too high, way much higher than what it was. And the question is asking which one is going to give us the answer that's too low. Okay? And for D, the vinegar is diluted with distilled water in the titration flask before NaOH solution is added. If I dilute this with water, I still have the same number of moles of CH3COOH, right? The NaOH molecules, the same NaOH molecules are still going to be looking for the CH3COOH molecules to interact with, right? So adding water to it isn't going to change my number. Cool? All right, so that takes us back to A, which was some of the vinegar was spilled out. And that was probably the most obvious answer. Any questions? Yeah? We skipped it. It's one of the problems we skipped. All right, number 12. Which piece of equipment would give the most precise delivery of 25 milliliters of solution? Is it a 25 milliliter graduated cylinder, a 25 milliliter syringe, 25 milliliter beaker, or 25 milliliter volumetric pipette? Anyone who's taken the lab want to tell us what the answer is? Volumetric pipette. Cool. Volumetric pipette is those things with like the cranks that you see people like taking DNA in and out of, like gel plates or with or whatever. So yeah, it's D for 12. What's up? Volumetric pipettes are probably the most accurate and precise way you can measure any sort of volume. I know it's unfair for you guys that haven't taken the lab, but the ACS just does a bunch of random stuff like that, and that could be a possible problem on there. This is also exactly how it's formatted, so just get used to like the font size and stuff like that. All right, 13 we're skipping. 14 we're going to do. All right, cool. The normal boiling points of molecular fluorine, chlorine, bromine, and iodine increase in that order. So boiling point increases when you go down. Increases as you go in that direction. Which of the following statements accounts for this increase? The chemical reactivity decreases in that order. The London dispersion forces increase in that order. The dipole-dipole forces increase in that order, or the hydrogen bonding increases in that order. Which one of these answers can you already eliminate? Is there any hydrogen in any of these? No, right? So it can't be D. Hydrogen bonding isn't happening. Next, dipole-dipole. Are any of these polar? No, if you're bonded to yourself, you're not polar. You're equally sharing. So you know it's not A and it's not D. I mean, it's not C and it's not D. Cool. And now I've got chemical reactivity and London dispersion forces. Which one of those two things talks about how will actually affect boiling point? Is it going to be the intermolecular force or something like chemical reactivity? Intermolecular forces, because that's intermolecular forces is what holds everything together, right? It's your internal, I don't know, it's like the internal framework for all of these, right? It's not how fast they react with something. I'm not measuring, like boiling is not reacting, right? It's just a physical property, right? And you got to look at the intermolecular forces. So it's London dispersion forces, not chemical reactivity. Cool, any questions? Did that make sense? All right, cool. So moving on to 15, we're doing it? All right, cool. So quartz, SiO2, is the most common mineral found on the surface of the Earth. What is the best explanation for the fact that quartz is hard and has a high melting point? SiO2. So, quartz crystals are extended structures in which each atom forms strong covalent bonds with all of its neighboring atoms. What does that definition kind of sound like? We were talking about network solids. Remember we were talking about diamond? Diamond, it's like 4 carbons and they're all covalently bound to each other. Yeah? So that sounds something like that would hint at having a very high melting point because like diamond is really, really hard, right? And very hard to melt too. So that sounds like something that could be the answer. B, quartz crystals consist of positive and negative ions attracted to one another. Does having a positive and negative ion necessarily make you like the strongest element on Earth? No, right? Sodium chloride, NaCl, that has a positive and that has a negative, right? If you're looking at water, the H's are positive and the oxygen is negative, right? Just because they're positive and negative doesn't mean it's going to have an incredibly high boiling point. So B is not an answer, couldn't be the answer. C, quartz crystals are formed under extremes of temperature and pressure. If something is created under extreme temperature and pressure, does that mean that its boiling point is going to be insanely high? Can you think of something that's formed under extreme temperature and pressure that has a relatively normal relatively normal melting point? No? All right. If you think of aluminum, like the aluminum foil that you guys use, in factories, they're using incredibly high temperature to melt all these alloys or whatever they're doing just to create that thin aluminum foil, right? Do you think aluminum foil could withstand the temperatures that quartz or diamond could withstand? Would you be willing to make a bet saying that aluminum foil is stronger than diamond? No, okay? So it's not C. Silicon and oxygen are atoms that are especially hard because of their electronic structure. That sentence just sounds like someone is trying to pretend they know stuff about chemistry, but electronic structure, we've never even said electronic structure, like ever. So yeah, it's A, which is the one that was talking about covalent network solids. Cool? All right, 16. The critical point of carbon dioxide is 304 K and 73 atm. Under which conditions is carbon dioxide liquid? Do you guys remember those phase diagrams where it's like, and it was like this was solid, this is liquid, and this was gas? Do you guys remember looking at this? Yeah, so this is something they're probably going to bring back. Do you know where the critical point is? Yeah, this right here. Okay, there's 2 points. There's 1 point here and there's 1 point here, okay? This point between the gas and the liquid, because after you get to this, right, there's pressure here and there's temperature. After you get to this point, the line here becomes really blurred. And there's some fluid here. Do you remember something called a supercritical fluid? Supercritical fluid. Just remember, supercritical fluid is ahead of the critical point. So remember that this is the critical point, okay? All right? This is the point where you could have like all three states probably, like maybe, like this is the borderline between solid and gas and liquid and gas and liquid and solid. Cool? This is the triple point, okay? Triple point, critical point, all right? So the critical point is 304 Kelvin and 73 atmospheres. So I'm at, let's say, 73 and 304. And it's saying, under which conditions is carbon dioxide a liquid? If we want to make it a liquid, do we want to go this way or this way? We want to go to the left, right? So we're probably going to want to make either, yeah, we're going to probably want to make either the temperature smaller, right, or the pressure a little higher. Yeah? Yes? All right, so looking at the possible answers, does anyone see an answer that could be it? Well, 1 decreases the temperature. We said if we decrease the temperature, we're going to go a little bit this way. It would be a liquid then, right? Yes? For the other one, 2, it says increase the temperature and increase the pressure. So you would go even further like this here, and you would end up in the weird supercritical area or the gaseous area. Cool? What's up? No, we want it to be liquid. We want it to be liquid. So the other one puts us in a weird area with either supercritical or gaseous. Cool? So it's 1 only. That's an option, right? Yeah, 1 only. Cool? All right. 17. Or are we doing 17? Yeah, we're doing 17. Okay. The lattice energy, which is the energy required to separate the ions in an ionic solid, magnesium oxide, is much larger than that of lithium fluoride. MgO, the charge of Mg is 2 plus, charge of O is 2 minus, is much higher than LiF. LiF. All right, I just put the charges there so you remember. So it's saying the energy required to break this guy up is much higher than it is to break this one up. Cool? And it's basically asking you why, or what contributes to this difference. So let's look at it. Magnesium is a smaller ion than lithium, and oxygen is smaller than fluorine. If you look at the periodic table, I think it's on the first page. Cool. What is going to be larger, lithium or magnesium? Looking at it. What's the atomic number of lithium, or atomic mass of lithium, versus the atomic mass of magnesium? It's 6.9 to 24.31. Cool. So that first statement that they said already is false. Magnesium is not smaller. Cool? Does that make sense? Just checking the periodic table. All right. Next, F is more electronegative than O. Lithium is more electropositive than Mg. Is that true at all? No, right? Cool. Let's see. C. MgO contains doubly charged ions, while LiF contains singly charged ions. Is that true? They do have double and single. So what does the double and single mean? What are those numbers up here? Those are charges, and charges, how many what's you have? Electrons, right? It's how many electrons you're sharing, all right? So Li and F are basically holding single hands, right? And magnesium and oxygen are holding two hands. Cool? So C is probably going to be the answer, unless D makes more sense. MgO contains more electrons than LiF. Do they contain more electrons because they've got a larger number? Does that mean that there's more electrons in it? That doesn't mean that there's... Yes, exactly. Cool. That just means the electrons that they're sharing. Cool. This number is not the total amount of electrons that they've all got in there. Cool? Does that make sense? Cool. So C is the answer. All right. Let's see. 18. We're doing 18. Cool. Which best describes the bonding in solid copper? Solid copper is in what group? What group on the periodic table? Transition metal, right? Okay, so with that in mind, let's look at the answers. The copper atoms are positively charged in a sea of delocalized electrons. That sea of delocalized electrons, that is a character trait of what? Transition metals, right? All of the transition metals, the reason they conduct electricity so well is because they're all bonded to each other, but their electrons are delocalized and freely moving around, which is why electricity is really easy to conduct through them, since they've got electrons moving all over. Cool? So the first statement is true. So that is probably going to be the answer, unless B, C, or D make more sense. The copper atoms are alternatively, positively, and negatively charged. Is a transition metal ever going to be negatively charged? They're all like pluses, right? Like copper, gold, silver, all of them got pluses. So B is false. The copper forms covalent bonds to adjacent copper atoms. That makes sense a little bit, right? It makes sense that they were saying that they would have covalent bonding. Yeah? So that's so far between A and C. We're going to have to discern between those two. And D, the copper atoms form hydrogen bonds to adjacent copper atoms. No, right? Cool. Let's see. Let's look at A and what is it? C, right? So A, copper atoms are positively charged in a sea of delocalized electrons. When you look at copper, it's, or any transition metal, right? There's going to be electrons flowing all around here, right? And all of these coppers are going to be positively charged, but there's going to be electrons flying around. Yeah? This copper is interacting with that guy, right? It's also interacting with this one. It's also interacting with this one. So they're interacting with everything that's all around them, right? Yeah? So C says only with adjacent copper atoms. Cool. So C is saying that they're only interacting in sheets. Do they interact only in sheets? Do transition metals only interact in sheets? No. Right? It's that there are solids that are interacting with everything and anything that's next to them. Cool. Adjacent, opposite. They're going to be interacting with whatever's above them or below them or next to them. Cool? Yeah? So A, positively charged in a sea of delocalized electrons. Cool? All right. 19. We're doing 19. A sample of 54 grams of methanol is heated from 25 Celsius to 35 Celsius. How much heat is required? And they tell you the specific heat capacity of methanol. So this is a heat capacity problem. Do you guys remember the specific heat capacity formula? Q equals M, I heard someone say it, cat, right? Q equals mass times specific heat times the change in temperature. Do we have all those variables in here? Yeah, we do, right? So we've got 54 grams. We've got the specific heat. And we've got the change in temperature. We went from 25 Celsius, we went from 25 Celsius to 35 Celsius, so we increased by 10, right? If you want to change that to Kelvin, you're going to have to change that to Kelvin since the specific heat value has Kelvin. But even if you change it to Kelvin, the difference is still going to be the same, right? If I add 273 to 10 and also add 273 to 25 and 273 to 35 and subtract both those two, the difference is still the same. Does that make sense? So this is just 10K. And what does this answer end up coming out to? You guys get 1340? You guys get 1340 doing it? Cool. All right. And 1340 is an answer, I think. Yeah. So C. Cool? So that was just a brush up of that formula. Any questions? Yeah?
Okay, so when you convert Kelvin to, Celsius to Kelvin, is it that you add 273
Yeah. So if change in temperature is final temperature minus initial temperature, right?
Yeah.
So if we did it in Celsius, it's 35 minus 25, which equals 10, right? If I add 273 to this guy,
But you add it to each individual.
and also add,
to the end.
yeah, right? Yeah. Cool. No, don't add it to the end. Yeah, that would be wrong. All right. Any other questions? No? All right. Let's move on to 20, which we're doing. Given the standard enthalpy changes for these reactions, calculate the entropy change for that final reaction they did. So we just did this recently, so yeah, you guys better know how to do this. All right? And what is essentially the main thing that I'm going to want to do? Oh, my God. All right. I'm just pretend that's not there. Okay. Yeah, so you got enthalpies. What are you going to want to do with those enthalpies? Hess's law. So you're going to have to flip stuff, multiply stuff, and then add them together. Yeah? You guys remember that? Cool. So look at what you want in the products and look at what you want in the reactants. In the products, I want to have P4 O10 solid. Does one of them have that in the products? The second one does, right? So the second one has it. And how about this? I'm just going to write it out so you guys can see this. P4 3O2 P4 O10 or P4 6. Yeah. This one is P4 plus 3, or no, 5O2. It's P4O10. And this delta H is negative 1640 kilojoules. And this one is negative 2940. And in the end, I want this. Yep, so I'm probably going to have to do what? Flip this one over, right? Because I need this one in the end, and I need that on this side. So if I flip that over, I'll have 3 oxygens over here and 5 oxygens over there. So if this is flipped, I'll flip it for you guys so you don't have to abstract think. P4O6 comes out to P4 plus 3O2. So if I flip that, I got to flip the sign here. So that's a positive. Yes? And now you can just look at stuff that cancels out. That cancels out there. Here I've got 5, and there I've got 3. So all these 3 will cancel out, and I'll only be left with 2 over here, which is what I have there. And I'll have this on the reactant side and this on the product side. Cool? So now I know I could just add these 2 numbers together. So what happens when you add these 2 numbers together? What number do you guys get? You get B? Yes? Cool. Everybody remember how to do Hess's law? Any questions? Speak now. Yeah?
If you had to multiply one of the equations by 2, would you multiply the chain by 2, or is that where?
No, multiply. Yeah, multiply by 2. Cool. If you had to, yes, question? I don't know which one to flip. All right, well, you just look at your final reaction or what you want. So I knew I wanted P410 in the products. One of them already had P410 in the product. So one of them already had some of the work done for me. But here, I needed P4O6 on the reactant side. So if you look at the first equation that they gave you, P4O6 is on the product side. So I knew I had to flip that one to get P4O6 on the reactant side. Cool? And this is what we did. We flipped this one. This one before used to look the opposite way. All right, so I needed to have this on this side. Cancel out P4, P4, 3 to 5, which leaves 2 over here. Cool, and this is on the end. All right. All right. We got, what, 21? All right, at what temperature is the following reaction at equilibrium when all substances are at standard pressure? Assume that entropies and enthalpies of reaction do not vary with temperature. They gave you delta H of formation values. They also gave you delta S, and they asked you something about temperature. What formula relates delta H, S, and temperature? G, right? G equals what? Delta H minus T delta S. Cool? When a reaction is at equilibrium, what does a G value have to be? What does a G value have to be? No, to be at equilibrium. Not to be spontaneous, it has to be negative. To be non-spontaneous, it has to be positive. To be at equilibrium, it's got to be a 0. Yes? Cool? So we know we got to set this guy to 0. Now let's find delta H and delta S from what they've given us. They gave us delta H for the products, and they gave us delta H for the reactants, right? And the total delta H is just products minus reactants, yes? All right, so I'm just going to do that here. So the product is PCl5, which is negative 374. So it's negative 374 products minus reactants, and the reactant is 0 plus negative 288. Question, if I had coefficients in front of either the products or the reactants, what would I have to do with the delta H values? Multiply them by that coefficient. Cool? But since there's only coefficients of 1 here, we don't have to worry about that. Cool? So I got delta H negative 85.3. Anyone else get that? Yeah? Negative 85.3. And this is in kilojoules. minus temperature, which is what we're looking for, times delta S. Delta S, again, is just products minus reactants, right? So I've got 223 and 311.6 on the reactant side. And so I've got 364.2 minus the products, minus the reactants. I got negative 170.4 joules. Anyone else get that? Negative 170.4. What's up? You guys got 86.2? 86.2? All right, cool. I'll listen to you. I probably put a number in. But for the joule value, did you guys get negative 170.4 joules? Cool. I've got to change it to kilojoules, right? Yeah? So how am I going to change this to kilojoules? Move it 3 places, right? So I can move this 1, 2, 3. And this is kilojoules now. Cool? So this is 0. I can just move that to this side. So I've got 0.1704 times temperature equals negative 86.2 kilojoules. There's also kilojoules. So now I can divide both sides by this. What does that temperature end up equaling? Oh, the supposed to be negative, my bad. Forgot the negative on that side. What does that end up being for you guys with a calculator? I'm getting 505.8. So temperature is 505.8 or 506. Everyone see how we did that? Yeah?
Why is 86.2 negative if you're adding?
No, I this state here, I added this whole thing to this side. Yeah, you see that? I added that whole thing to that side. Cool? Yeah? Delta H is all the delta H's of the products minus all the delta H's of the reactants, right? So they gave me the delta H of the product PCl5, which was negative 374. And then all the delta H's of the reactants were the delta H of PCl3 plus the delta H of Cl2. Delta H of PCl3 was negative 288. Delta H of Cl2 was 0. So essentially I did negative 374.9 minus, in parentheses, negative 288.7. Cool? The main important thing to remember in this problem, you couldn't have done this problem at all if you didn't know that delta G had to equal 0 at equilibrium. Cool? So that's important to remember. Delta G equals 0 at equilibrium. Cool? All right. All right. 22. Given the bond dissociation enthalpies below, what is the approximate heat of formation of H2O? Cool? So they gave you HH bonds, OH bonds, O bonds, and O double O bonds. For H2O, it's just this, right? Yeah? So I've got 2 OH bonds. So I need to take the number for OH, first of all, and just multiply it by 2, right? Since I have 2 of them. Yeah? Okay. So 467 times 2 is what? What's up? 934. Is that an answer choice on here? Cool, yeah. That's a possible, right, answer choice for this. So in water itself, I've got what? 934 in water. Cool? That's in water. Yes? Yeah? Okay. So when I want to form water, what do I have to do? I did not leave enough room. Do it up top here. I gotta balance this out. Cool. All right. So I know that this in the end here has 934, right? This thing has 934, so 2 times 934. Cool. And they want the heat of formation of O2. So if you want to find the heat of formation of O2, we've already found the bond energies in here. So it's the same thing for delta H or for delta S or delta G values. Total products minus total reactants. Does that make sense? Yes? Total products minus total reactants? Okay. Yeah, all right. So we have two H2 bonds. Do we have an HH bond number here? Cool. Do we have an OO bond number here? And I've only got one of them, right? Can these O oxygen, like when oxygen binds to H2O, it makes 2 bonds, right? It makes one with one H, one with another H. What's the charge of oxygen? -2, right? So you're probably going to be sharing how many electrons? 2 with each other, right? So if you're 2 with each other, you're going to make double bonds. Cool? All right, so we'll use the double bond number, which is 495. Cool. And we'll do all these minus all of that in a calculator. You guys getting negative 255? Yep. Did you guys get negative 255 in your calculators? What'd you get? 510, are you sure? I'll do it again. On 2 times 934 minus parentheses 2 times 2 plus 495 13 minus 2 times 934. How are you guys getting 509? Yeah. All right, okay, just leave this here for now, because we got to make sure we do all the other problems too. But this is just, everyone knows how to do this problem, right? You just add the numbers up from both sides and just subtract them. The process is completely correct. I guess there's some sort of disconnect with numbers, but yeah, cool. But everyone understands what Hess's law, how to do Hess's law with like multiple reactions, and how to do products minus reactants for the sums, right? And multiply by molar coefficients. That's all I need to make sure you know. Cool? All right. Yeah. Yeah, question? We made that for H2O. Like for the product, since H2O is 2. Okay, cool. Yeah, all right. 23. Which of the following are true for a spontaneous process in a system at constant temperature and pressure? It says the entropy of the system plus the entropy of the surroundings. What is that when you do system plus surroundings? It's universe, right? And entropy of the universe is always increasing, always positive. So it says system plus surroundings is greater than 0, which means positive. So that one is true, right? And the statement 2, delta G of the system is negative. When delta G is negative, is it spontaneous? Yeah, cool. So it's statements 1 and 2. So that's C for 23. Delta S of the universe has to be positive to be spontaneous, and delta G of the system has to be negative. Cool? All right, number 24, we're not going to do that one. It's going to take too long. But it's just using the G of formations of all the products, and which is what they're giving you, and it's that formula that relates K to G. They don't give you that formula in here, so I just figured don't do it. But all right, 25. Elemental bromine. We're doing this. Okay, yeah. Elemental bromine is being formed according to the equation at a rate of 0.056. So it's okay. Yeah, it's way too. Everyone has this sheet, right? Does everyone have this? No? Oh, okay. I'll write it out then. 5Br plus BrO3 plus 6H makes 3Br2 and 3H2O. And they're saying this guy is being formed at a rate of 0.056 m. Cool? So at what rate is the bromide ion right here being consumed? How are we going to relate those two? Let me do the answer right now. Check it before we do it. Make sure it's right. Yeah. Yeah, cool. Okay, so if I have the rate for this one, and I don't have the rate for this one, I want to relate molar coefficients, right? Yeah? So if I'm going at this rate for Br2, what's the molar relationship between Br2 and Br? 5 to 3, right? There's 5 Brs for every 3 Br2s. Yeah? So times 5 Br over 3 Br2. So this number times 5 divided by 3 is what? I got 0.093. Please tell me you get that one this time. So I'm going to have a heart attack. You guys getting 0.093? Okay. Whew. All right, you guys see why, like how that worked? You just relate all the coefficients. If they ask you for H, what would you have made the ratio? 6 to 3, right? You would have made it 6H over 3Br if they had asked for the rate of disappearance of the H. Cool? Yeah? Okay. Moving on to number 26. Cool. A radioactive isotope used to image the heart has a half-life of 3.05 days. How long would it take for a sample of thallium to decay to 18% of its original activity? Do you guys remember how to do the half-life equations? We don't remember any of the half-life stuff? Okay, so I don't mean like the first order, second order, just in general, how you would figure out a half-life. Okay, so what it is it's 1/2 raised to whatever the half-life is, yeah, times your starting the original sample, like original mass or whatever, will equal the final mass. Cool? This is how you figure out half-life. And you put that actual half-life in here. So I want it to be at 18% of what it originally was. Cool? So I'm going to take this over and put it over here because that's what the original is. So 1/2. What's the half-life in this equation? 3.05 days. Yeah? Okay. Cool. And here, we're going to want it to be what? Final over original. And final over original has to be 18% or 0.18, right? So this ratio has to be 0.18. Cool. That ratio has to be 0.18. All right. So this number here, x, I don't know how many half-lives are going to happen yet. Yeah? Okay. Don't know how many half-lives are going to happen. This is what I need to figure out, this x. So when I have a number raised to an exponent that is unknown equals another number, what do you have to do? Remember log rules? Yeah, log base 10. So here, let me erase. I'm going to erase this, okay? And this has to equal 0.18. So this is log base. Okay. Log base 1/2 upper 0.18 has to equal my x value. You guys remember how to like set up log stuff like this? It's whatever the number is raised to the exponent to, that's what goes on the bottom. Whatever it equals is up here, and the exponent is always the answer over there. Cool? So if you do that in your calculator, you can't do that?
Yeah, I think the look in the calculator, we can't change the base.
Okay. I guess you can. Okay, so if you can't change it on your calculator, that's not a problem. Because now you can just do it by like assessing your answer choices and then eyeballing what it could actually be. Cool? So if this is 0.18, this x value up here, it can't be something like 10, right? Because if it's 1/2 raised to the 10, it's going to be 1/2 raised to the 10, and that number is way smaller than 0.18, right? So if we do 1/2 to like the 2, right? 1/2 squared, that goes to 1/4, right? If I do 1/2 to the 3rd, that goes to 1/6. Yes? So 1/4 and 1/6. 0.18 lies like right between there. Yeah? So you could guess your exponent would be something like 2.5. Okay? Yeah?
What you do if you can't do it on a calculator, what you do is you do log times 1.8 and then log times 0.5, and then you divide log 0.18 divided by log 0.5, and it gives you. That's
Okay.
the change of base, how do they change the base?
Okay. What's up? Okay, yeah. So I guess you just need to remember the change of base formula. Cool? All right. So yeah, even if you didn't want, you just have to eyeball. Let's just say we eyeballed it and we guessed it was like 2.5, right? So we guessed that that x number is 2.5, and x is the number of half-lives, right? So 2.5 half-lives. And our half-life is 3.05. If I multiply 3.05 times 2.5 half-lives, that's like 7.6. And is one of these answers close to that? Yeah, 7.5. Okay? So it's C for 26. If we guesstimated that the X was 2.5 half-lives. Yeah? That's the number of half-lives. And the half-life value is 3.5 days. Yes? So if I have 2.5 half-lives, I need to multiply 2.5 times 3.05, because that's the length of my half-life. The X is how many half-lives over you're going to repeat. If this was 10, that means it would be 10 of these. Okay? This X number is the number of half-lives that occur. Any questions? X is the number of half-lives that occur. I'm just going to write the formula one more time, and then we'll move on to the next question. The formula is 1/2 raised to the n, and n is number of half-lives, times the mass initial equals your mass final. Cool? Just make sure you remember this formula. Yeah? Oh, well, I mean, we knew that 1/2 raised to the n had to be 0.18. If you didn't remember the log of base formula, if you like blanked, then you could just go ahead and put numbers in here. I put 1 in there. 1/2 does not equal 0.18, right? If I put 2 in there, it equals 1/4. And 1/4 is a little bigger than 0.18, right? If I put 3 in there, it's 1/8, right? And 1/8 is much smaller than 0.18, yeah? 1/8, an eighth. 0.18 is like almost 0.2, which is a fifth. Yeah, so you knew that it had to be between 2 and 3, so we just guessed 2.5. Cool? All right. Okay. Moving on to number 27, and let's it go. So we're going to do that one. For the reaction, the following data was collected. And it's just a chart with the rates, and it asks you to find the rate law. When you want to find the rate law and they give you a chart like that, what are we going to do? You pick two experiments where one reactant is the same, so it doesn't matter, and you relate the concentration of the other reactant with the rate law. Okay? So let's go ahead and check it for the chromium compound. All right? So on the other side, the second and the third experiments are the same for the other. So we can do 0.028 over 0.037. Raised to something has to equal those rates related to each other, and those rates were 1.1 times 10 to the negative 5 and 1.5 times 10 to the negative 5. So essentially the same thing. Cool? 0.028 divided by 0.037 and 1.1 times 10 to the negative 5 over 1.5 times 10 to the negative 5. What are those ratios? 0.028 divided by 0.037. That's 0.756. And 0.1 divided by is like 0.73. Yeah? In this problem, these two numbers are close enough to each other for us to say that this number up here is just 1. And if I put that number 1 up there, what does that number 1 represent? First order, right? So I know that our formula has to have chromium with a 1 exponent next to it. Cool? So now we do the next one. Which is for sulfur cyanide. And we can do experiments 1 and 2. Yeah, you have to pick the experiments where the values are different for it and the other one stays the same. So we can cancel out. So experiment 1 and 2, the chromium goes from 0.028 to 0.028, so we know that it won't affect the rate change. All right, and this one is 8.1 times 10 to the negative 6 and 1.1 times 10 to the negative 5. Cool. So this number ends up being 0.04 by 0.055 equals 72. Raised to some number 8.1 times 10 to the negative 6 divided by 0.1, 2, 3, 4, 1, 1. This number is like 0.73. So again, we can just assume that this thing is just a 1. So we know that SCN has to be a value of 1. Yeah, first order. So both of them are first order. In total, it's a second order. So we know it's answer choice A or B. Yeah, so it can't be C or D, because C and D suggest that SCN is 0 order. So now you've got to figure out the rate. Cool? And to find the rate constant, you just plug in stuff. So let's plug in the information for experiment 2, I guess. So the rate for experiment 2 was 1.1 times 10 to negative 5 equals K. Concentration of chromium was 0. Cool. Concentration for chromium was 0.028, and for the other one it was 0.055. When you do algebra and solve for K, K ends up being 7.2 times 10 to the negative 3. Yeah? What's up? You could have picked any random experiment. You could have, like, to find the K, you could have picked any experiment and plugged in the rate and the concentration for those two things. Cool? I just picked the middle one. You could have picked any other one. But any other one will also give you the same K value, which is 7.2 times 10 to the negative 3. Questions? No? All right.
Why do we have to do the whole first part again?
The whole first part is to know that this guy is raised to the 1 and that guy is raised to the 1. Cool? Like the first part was determining the orders of each reactant. If this guy was, because there's multiple answers in there where the order of SCN is 0 order. And we had to make sure that SCN wasn't 0 order. Cool?
So the rate law is like, rate law is equal to K times the reactant times the reactant?
Yeah, reactant times reactant, and each reactant is raised to their respective orders. Cool? All right. 28. All right, 28. Which of the following ways may a catalyst increase the rate of a reaction? 1, it may alter the rate law, and 2, it may decrease the overall activation energy. One of those two, without discussion, you should just know, like by memorization, that it is. Which one of those is it? Second one, right? It lowers the activation energy. Activation energy is that hump in the energy curve, so it lowers that curve. So it has to have 2. So we know it's not A and it's not D. So now we have to check if 1 is true. It may alter the rate law. The rate law is what? What is the rate law? We just wrote it. What's the formula for rate law? Rate equals K times one concentration of a reactant times another concentration of a reactant, right? That K, what was that? What are, like, just go ahead and look back in number 27. The units for K are in what? There's a concentration per hour, right? Concentration per hour, the rate is how fast something goes. Do catalysts change how fast something goes? If it's lowering the activation energy, that means it's allowing it to move quicker, yes? It's not participating in the reaction, it's just allowing the reaction to happen at a faster rate. Cool? So it's 1 and 2. C. Any questions? No? All right, so let's go to number 29. For an exothermic reaction, which of the following best describes the effect of increasing the temperature on forward and reverse reactions? So let's just, before we read those, let's just write out an exothermic reaction. A plus B is C. If it's exothermic, it's producing heat, right? Yeah? It's producing heat. Yes, because this is what exothermic is. All right. So let's look at the answer choices. Increasing temperature, so you're adding more of this. For increasing temperature, both the forward and reverse rates increase, but the forward rate increases more than the reverse rate. If this is a seesaw and you add more weight to one side, is it going to continue shifting to that side? If this is imbalanced like this, if this side becomes a little heavier, the reaction is going to want to move backwards to bring it back like this, yeah? So A is false. B, both the forward and reverse rates increase, but the reverse rate increases more than the forward rate. If it got tilted this way, is it going to want to go a little bit more to the reverse? Yeah, so B is true. Let's look at other answers. The forward rate increases while the reverse rate decreases. Is that going to decrease? No, that's not true. And D, the reverse rate increases while the forward rate decreases. Is it going to change the forward rate, or is it just going to make the reverse rate a little faster? A reaction can, this is it here, at equilibrium, a reaction can never prevent something from happening, right? When it does equilibrium like management, all it is essentially is damage control, right? Because in physics, or like in physical chemistry, whatever is reacting on the inside, there's no like crossing guard that's holding a stop sign for A and B and telling them not to go forward. These guys are still going to be reacting, right? And what D is saying is that this arrow, forward arrow, is just going to stop. And there is no situation ever where molecules will like stop for the sake of organization. Cool? All right? So the answer is, what did we say? B, right? Yeah, B. Cool? Any questions? This is actually a question that actually might pop up on the test tomorrow, because I remember when I took this ACS for Chem 2, that a question almost exactly like that was on there. So make sure you remember it. Okay, 30 we're going to skip, 31 we're going to skip, 32, 33 all the way, because those are not going to leave us enough time at all. Let's see. Number 34. All right, this is something that you guys do need to remember, though, because they'll probably do it on the exam. And it's, what is that curve that's on there? It's a titration curve, yeah? So it looks like this. We're at 12, 14, and there's 0, 1, 2. Cool. It starts off up here. And let's say that this is 7. And goes like this. So its equivalence point is like right here. Yeah? It says 1 gram of a weak base is titrated with 1 molar aqueous HCl to give the data shown. What's the identity of the base? And what it gives you for A through D is pKa values and whatever base was. Cool? So if you want to figure out the pKa for whatever was being titrated, what you need to do is you go to the moment right before the equilibrance, right before the equivalence point where the slope was 0. Here the slope is undefined, right? Yeah? Because that's what the equivalence point is. Equivalence point is slope is undefined. Where the pKa value is where the slope is 0, right here. So if you go to that number, here I think it's like 9.5 or 9. It looks like somewhere where it's like near 9, right? Does everyone see that on the curve? Does everyone see that on the curve? like 9, and it's like to the lower half. It's like, yeah, somewhere to the lower half of it. So if you go now at that number, at the lower half, this is the pKa value of whatever's being titrated. Of, in this case, the base. Cool? So now you look through your answer choices and you see which answer choice has a pKa closest to that. So A has 9.3, which is probably close. What's up? D is 9.8. If you look at the graph, 9.8 would be very close to 10, yeah? Is the slope at 0 close to where 10 is? Is it closer to where 10 is, or is it closer to the middle between 8 and 10? It's closer to the middle, right? 9.8, it would have had to have been much higher. Do you have the thing with you? Okay. So yeah, this is why you guys probably should have brought this, but who doesn't have it? Okay, yeah, there's way too many people to pass this around. But look next to someone who has it and just show it to you. They'll show it to you, but this number is very much closer to 9.3. Cool, so just remember that pKa values are where the slope is 0, okay? Make sure you remember that, because that's probably going to be tested. What's up? 9.3. Cool? So remember that. pKa, slope is 0 right before there, right before the equivalence point. I don't think you guys covered that at all in class, right? No, yeah. All right, we're going to do 36. Which of the following will increase the concentration of chloride ions in a saturated solution of AgCl in contact with excess solid silver chloride? Oh, okay. Yeah, all right, so what do we know about solubility in a situation like this? If the solution's saturated, right? If the solution is saturated, if I'm adding more of the same members into that solution, is it going to make it more soluble, or is it just going to make it more crowded in there with the same ions? It's going to make it more crowded, right? I remember seeing the videos of the supersaturated solutions of like some salt, and they drop like a pellet of salt in there, and it just crystallizes, and it becomes solid. Solids, if it forms a solid, that means you're lowering solubility, right? So you need to add something else that has nothing to do with it, yeah? So one, it says add more silver chloride. If you add more silver chloride, you're adding more of the same ion, therefore reducing solubility. But if you add NH3, something completely different, it's going to allow the chlorine ions to dissociate and be their own thing, not be part of a solid. Cool? So it's 2 only. Any questions?
But if you like wrote it out, you write AgCl and then like the equation,
Mm-hmm.
and then Ag plus Cl minus. So if you added more AgCl, then it would push the reaction, right?
The key is, though, that it's saturated. That's what you need to understand. Because at saturation, that reaction is not going to want to go forward at all anymore. Cool? Anything before saturation, if you're adding more, then yeah, you're going to keep making those ions. But once you've reached the saturation point, once you reach the sealing capacity for the chlorine ions, they're not going to want to make even more. They're going to want to be able to dissociate. Cool? Does that make sense? NH3 is a member, like there is no nitrogen in silver chloride, right? There's no hydrogens in silver chloride. If you add NH3, something completely different, you're allowing for more room for the AgCl and more space, essentially, and more, you're disturbing the interactions between the Ag and the Cl. So they're not going to be able to bond together. They're going to want to dissociate more. And that's exactly what you want, because you want chloride ions. You don't want solid silver chloride. Cool?
So it's just 2?
What's up? Yeah, only 2. All right, 38. Cool. Which of the following substances is chlorine in the lowest oxidation state? I've got Cl2, KCl, KClO, and KClO4. All right. Chlorine, what's the oxidation state here? 0. Here, chlorine is what? Potassium, we know since it's group 1, it's always positive 1, right? This was negative 1, yeah. Here, we always know potassium is positive 1. We know oxygen is always negative 2. So this total charge, right, on KClO is what? Neutral, right? So that means chlorine in this case has to be, if this guy's negative 2 and we only have 1 plus, to balance out the negative 2, we need what? Another plus, right? So now here, chlorine is plus 1. Yeah? And in KClO4, this is plus, this is negative 2. So here, there's 4 oxygens, so in total I have negative 8 up here. So a positive plus a negative 8 plus something else has to end up equal 0. What does chlorine have to be in this case? Positive 7. Yeah. So the lowest oxidation state is what? Lowest? Lowest number. -1. Cool. Yeah? Makes sense? Lowest and highest would be what? Cool. All right. Okay. Just give me 39. 40. Cool. What is the cell potential for the following reaction? Cell potential for the following reaction, and they give you 2 half cells, right? 1 half cell is the reaction up here is and they give you the reduction potential is negative 1.66 volts and negative 0.76. So which one of these are we going to have to flip? If you don't do it by looking at these numbers to decide what we're going to have to flip, if you don't know how to do that trick, just look at the reaction up here, right? Yeah. To like flip, it's with, all right, we'll do that one after we'll do like the very first one, all right, cool. So the first one here, if you want to do this reaction, what does it kind of show you, the one that you're going to have to flip? What's it? Why? Occurs in the opposite direction, right? So if you flip this, then what does this value become? This value becomes positive. And then you do what? Why not multiply, though? Why not multiply by the molar coefficients? Why do we flip this one? Because solid zinc has to be in the reactants, and here solid zinc is in the products. So you know you got to flip this one. Does that make sense? Why don't we multiply when we're doing cell potentials? Do we multiply by coefficients when we do cell potentials? Yes or no? No. All right, cool. You don't multiply by them because The cell potential that's the electrical potential, so the potential for any of these molecules to either give or take away an electron. That potential doesn't change with however many there are, right? It doesn't, like, if you have, let me think of it this way. If you're asking some, like, kindergartner to give up his graham crackers, right? That kindergartner is not going to want to give up his graham crackers whether there's one kindergartner or like 50 kindergartners. They all want their own graham crackers, right? It doesn't change based on how much you want. That's what electrical potential is. It's like your willingness to give away an electron or take in an electron. Cool? Right? So when you add these two together, what do you get? Negative 0.9, I think. Yeah? That's the answer. All right. What is, someone asked me a question. Yeah, you asked the question to flip. Yeah? To flip. When you want to flip, you have to flip the one so that when you add it, you get a very negative cell potential. Cool? So if I flip this one and added it to there, it would still be positive. And you want your E cell to be negative. Cool? Yeah?
What were you solving for when we were using coefficients?
Before, yeah. We were using coefficients for delta H, for delta S, for delta G, for bond enthalpies, yeah? Like what you want for a cell potential? Yeah, yes. Cool. Yeah, exactly. One is always going to have to get flipped. Cool.
What does negative cell potential mean?
What's that?
Like, what does negative cell potential versus positive cell potential mean?
There can be like negative, if you have a negative cell potential, then that cell is probably going to drive in like the direction that you want it to drive in. If you have it in a positive direction, it's not going to go in the direction that you want it to go in. Cool? Yeah. If you want to think about it that way, then it works. Cool? All right. What number are we on now? 40, 41. We're not doing 42 through 46, 47. All right. This is something that I know you guys didn't do in class. When talking about decay, you didn't really go into it in detail, right? You guys remember radioactive decay? No? All right, cool. So that's probably going to be on there. All right? So radioactive decay is, there's three kinds. This is stuff where like you get into like nuclear chemistry, stuff like that. It's pretty cool because that's when an atom or an element can lose either electrons or lose protons or gain electrons, and it can become an entirely different metal. So it's almost kind of like magic a little bit. Cool? So there's three types that you have to remember. There's alpha, beta, and it's called gamma or positron. Gamma or just positron. Cool? All right. Actually, no. Gamma is something. Here, let me write this down for you. I'm going to put it up here. Yeah. So alpha is you have a number with an atomic number and a mass, and it goes to the atomic number -4 and the mass number -2, and it's some new thing. For beta, goes to the same atomic number, but the mass number is added by 1, and there's a new thing. Cool? And for right here, let me get the last one written down. The last one is gamma, but the other one that you actually really need to know is positron, because this is what they're going to test you on. Positron allows the atomic number and the bottom to stay the same, but for some reason, which is losing, there's like a positron emission. It's like they shoot it with a proton, and the proton, because it shoots that element, it disturbs like the balance of the shells, but it doesn't disturb like the actual numbers. So it basically changes the shape of the atom. Because it changes the shape of the atom, it can take on a whole like completely different like characteristic. Cool? So let's look at the choices here. It goes from 52 Mn to 52 Cr. Cool? Oh, I forgot to do gamma. Damn it. All right. Just remember that positron is the same stuff, just it looks different, because I'm going to write gamma right there. And positron is the same but different. Cool? Okay, so it goes from manganese to chromium, but it still has the same atomic number, right? And what do we say when it changes an element, but it's still the same atomic numbers? Beta, if they wanted to notify you that the mass number had changed, they would have put the mass number there. So you can assume that the mass number stayed the same. So in what case does the mass number and the atomic number stay the same, but it changes to something different? Positron. Cool? So 47 is C. All right. Okay. We're not going to be able to do all of these because we still have to leave like a little 5 minutes for the debrief. All right, 50, that's geometry, right? It's a geometry, like molecular geometry stuff. So make sure you just look over like the charts. I want to do number 51 because I know you guys, I don't think you guys did that in class. But 50 is just geometry. Is everyone fine with just skipping geometry stuff? All right, so 50 is geometry and 53 is geometry. So both of those are just definitions. Let's do 51 because 51 is very important. It has to do with pi bonds and sigma bonds. Does anybody know what a pi bond and a sigma bond is? It has something to do with double bonds, single bonds. Excellent. Cool, right? So here it says our structure is H2, double bond CH, single bond CH, double bond CH2, right? So when you see that, just draw it out. So I've got CH2, double bond CH, single bond CH, double bond CH, and H. And it asks how many sigma and how many pi bonds are there. Cool? Remember that sigma bonds are just the single bonds. One line. Cool? All right? Anything after one line is a pi bond. So it's the single plus extra. And if that doesn't make sense, it'll make sense here when I do it now with this. So this single bond right here, this is just a sigma. Cool? This single bond right here is a sigma. All right? This single bond right here, that single line is a sigma. Anything after you count 1 is a pi. So now this is pi. This here is just a single one, so it's sigma. This here is sigma. Anything after sigma on the same thing is pi. This is sigma, and that is sigma. Cool? If something was triple bonded, how many sigma and how many pi bonds does that have? 2 pi, 1 sigma, because you always count the first one, sigma. Anything after that is a pi. Pi and pi. So there's 2 pi's. Yeah, and if it's triple bond, you have sigma in the first one, and then pi. Cool? Make sure you remember that, because they were probably asked that. So now I think it's total 1, 2, 3, 4, 5. Oh, we forgot these. Sigma. 2, 3, 4, 5, 6, 7, 8, 9 sigma and 2 pi. Is that an option? Yeah, C. Cool? Does everyone understand sigma and pi bonds? Yes? All right, good. So that pretty much does it. 50 and 53 is just memorizing geometry. Make sure that you guys don't only do this. This was mainly to help you guys get right, like prepare for the wording of how the problems are usually worded and the structure, because it's very different. I recommend still brushing up on like principles that you guys need to do. Make sure that this isn't the only stuff you do. So you have a whole week. Do it slowly. If you guys want to come up and scan this sheet here, it's basically allows you to do a survey to just for how like the entire study union process went for you. If you want to come up and scan it, please do. Otherwise, yeah, that's it. Thank you for coming and good luck studying. There's going to be other Chem 2 sections. Other Chem 2 sections. Yeah, on study union session.
So no class on Tuesday?
No class.
Thursday at 7 for the final.
Yeah. All right, let me count this.